wait. Where are my students?
Good morning. I'm the last one.
Maybe someone joined. How can you know? Nothing is sure today. Okay, where is my... I need to put a link online. Maybe someone wishes to join us from home. From workplace. From somewhere. Things happen. Okay. I have new demo for today, brand new. New object. Never seen before. Okay. We can start and see what happened. What I have for today. What I have for today is called pulse modulations. The idea is to use pulse sequence, starting idea, to use pulse sequence to transfer something, information, sound, so on. The first one from the pulse modulation is an amplitude pulse, APM. Amplitude already opens idea. Pulse amplitude will be used, let's say, to encode information. Let's say we have a harmonic signal like sine omega s. And pulse sequence. So it's about 0, tau 1, tau 2, and repetition time t capital. So this moment is tau 1 3 plus t, and this moment what I'm doing, tau 1 plus, and so on. So we have a pulse sequence, and we want to use this pulse sequence to transfer our harmonic signal. Why harmonic?
Sorry for being
harmonic for simplicity. So I have something like S max sinus common signal will be S max 1 plus modulation depth sine t and 0. This one is in force when minus tau plus well, maybe time tau plus m period and 0 tau by half plus m t time tau by half plus m plus 1 time. I can draw it so like this. It original pulse sequence and it will be this one sine omega st. Resulting, I'll show it in blue, pulses with amplitude subject or changing by the law of signal. Where you can find such signal? It's not let's say it's not very common in life. Such kind of signals produce image sensors, but it's already processed. Today, barely you see something like this. Or analog to digital converters after sample and hold or prescaling when you need to deal with wide range signals, like power system where from normal mode to fold 40 times. When you deal with such kind of signal, common analog to digital converters don't have sufficient range, often don't have sufficient range, and schematics include prearranging device, like 1 to 1, 1/4, let's say 1/16 control divider. After pre-scaling unit, you may see amplitude modulated signal. For amplitude modulated pulse amplitude modulated signal, spectrum so signal can be written as S maximum 1 plus modulation depth sine omega st multiplied by tau divided by repetition time, and it all should be multiplied 1 plus sum where n changes from 1 to infinity sine n omega s tau divided by half and divided by n omega s tau by half, and all this should be multiplied by cosine n omega s tau. Quite terrifying. Look, it should be simplified with the help of trigonometry. We will get something like this, equals to S max tau divided by pulse repetition period multiplied 1 plus modulation depth sin omega s plus double sum where n changes from 1 to infinity sine n omega s tau by half divided by n omega s by half. This also should be multiplied by cosine of n omega s plus modulation depth by half sine of n omega s plus omega time minus modulation depth by half sine n omega s minus omega time up. Looks awesome. The most I see error. This should be I, this should be I. And 1 second, I will explain. The moment is what? Omega I is I double P divided by time. It's a point of, we will have discrete spectrum, and this discrete spectrum has values only in some particular points. Let me draw it. It's quite complex. It's very easy but to understand it, better I draw an example. What's the idea? See, you will have spectrum like this. You will see lines. This is omega 1 divided omega 2 4p divided omega 3 and so on. It's like a grid or mesh of the discrete frequencies. Outside these frequencies, you see nothing. It's when you have unmodulated. Remember pulse sequence? It's second or third direction. We saw a discrete spectrum on the set of lines. These are lines of unmodulated spectral lines of carrier sequence. When we add our signal, we use amplitude modulation of sequence. We will get these things. This is omega 1 plus omega s. Omega 1 minus omega s. We will see a line at the frequency omega s. This line, omega 2 equals to about omega 1 plus omega s. This one, omega minus omega s. Omega 3 plus omega s. Omega 3 minus omega s. And in this way. But that's not all. If you take a closer look, you will see something. Something in different scale. You will see an interesting picture. Decaying line, this line is something like sine x divided by x. Set of decaying wave. And inside there will be a kind of triplets. Inside you will see a kind of triplets, discrete spectrum lines from the carrier sequence and side lines from carrier signal. This kind of signal, this is omega I plus omega s, omega I, omega I minus omega s. Where's the problem with such kind of signal? It takes a very broad spectrum. It is not optimal. It's far from optimal. When we speak of communication channel utilization, it takes a broad spectrum, in fact useless. See where's the problem? Each of the red line has all information about transferred signal. It's a reality. When you try let's say you have signal, let's say taking this frequencies from omega min to omega max. You need to transfer signal with the spectrum from omega minimum to omega maximum spectrum. You will get whoop, 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 omega 1. I should draw it in white, sorry. Omega 1, omega 2, omega 3, omega 4, and so on. And around will be this spectrum. Spectrum of transferred signal will be around all these discrete spectral lines. You will not be very happy with such kind of signal when you will speak on communication channel utilization. Another way how to encode a signal in a pulse sequence is pulse shift modulation. Let's say you have a sequence with the period. Period will be a function. So pulse will be shifted so period will be a function of transferable signal. You can shift.
That's how the flip-flops work, right?
You know what's the closer? Signal from the zero sensor of the internal combustion engine or ignition. Where it's pulse shifted. Ignition pulse is shifted relatively to the 0 point as a function of RPM, of rotation speed. It's one version where the period is shifted. And another version, extremely popular. Here we have shift within a period, small. But we can also do a different thing. Very popular mode is in the version of shift, impulse length remains the same. Another version is when we have, let's say, tau 1, tau 2, tau 1 plus period, tau 2 plus period, when length of the pulse is a function of signal. Such version is called PWM, pulse width modulation. Note that in the first version, timing between pulse is shifted. Here, timing remains the same. Is constant, but changes width of the pulse. If we speak on spectrum, we speak on spectrum, such sequence can be described in mod form as maximum tau divided by impulse sequence time minus this is T max divided by tau sine omega s by half. This is for case we use one sine for the sequence is modulated by one pure sine. When not explaining when we shift pulse, Tm will be timing between previous pulse and the next one maximum possible. This Tmax is a maximum allowable shift of the pulse front. This must be multiplied by cosine of omega signal time minus t by half plus sum where m should from n from 1 to infinity, 1 divided by np multiplied by sine n omega I t plus tau by half minus t sine omega s time. That's not all. Minus sine n omega I time minus tau by half minus Tm sine omega s t minus tau this can be converted into this should be converted into something like this it can be replaced as maximal tau divided by pulse sequence period minus double T max divided by time sine omega s tau divided by half multiplied by cosine omega signal t minus tau by half plus sum n from 1 to infinity of sum where m change from minus infinity to infinity double and p multiplied by the Bessel function of m using phi as the max omega I. It's a Bessel function. Sine n omega I plus m omega signal divided by half, and this also should be multiplied. I will continue here. It should be multiplied by cosine of m omega signal plus m, sorry, this will be I and this will be signal. Tau minus m omega signal. This is end. Looks terrible. So, if you have a sequence of the pulse with the repetition period of time and its width being function of signal, you will get spectrum like this, borderline, something like sine x divided by x, omega 1, double omega 1, triple omega 1, 4 omega 1, and so on, and around multiple spectral lines of they are repetitions of original modulating signal. And now question, why do we wasting time on this formula? It should be a reason, isn't it? The question, the question is good. And the answer, exactly this signal now all around us. It's become a course of modern power engineering and electronics and so on. It's a key element. You know what this is? It's called clock. It's a key moment of today power measurement. and power efficiency. Very simple example, step-down converter. Have you heard? Simple example, I want 24 volts converted to 12. DC. Let's say 24 volts. Switch. It should be field transistor or simple transistor. Coil to introduce in a filter capacitor. Load. Someone need to control switch. Pulse width modulator will control it by the feedback signal. How it works? It's a moment of today's power control. Have you heard something about it? This is capacitor to explode. Don't I have some disused motherboard here? What's here? Oh! For example, old video. Here's the cool. Yeah, repeat. Coil, switch. Another one under the radiator. Coil and these are FET transistors. Older version may use bipolar. It's not important. Here it is. Power converter. Idea of PWM. Take a voltage like this and compare it with the necessary load voltage. What will we get? Sequence of pulse. This is pull out. Switch on, switch off, switch on, switch off, switch on, switch off. What will happen if, for example, load decreases and voltage rises? We will have shorter pulses, but with the same frequency. Coil receives less energy, and what will happen with the voltage? It will go down. Let's say is smaller. What will happen? Wider pulse, more energy. More energy, voltage will go up. Here is my DC to DC converter. Voltage. Come here. what I got here? This one is supply voltage. This is supply voltage. This one is supply current. Load current, load voltage. And this analog meter, supply current. And where is my, I can switch, wait a second. It's a coil voltage. Supply, switch, discharge diode, not to kill, capacitor, air load. Pulse width modulator, U, load or feedback signal, and control signal. I took this voltage, it's a yellow line. To make it more visible, maybe I'll switch to average mode, it will freeze. Hey, come on, I want to freeze you. It's an average instant. It's like this. You can see pulse width already changes. It's not ideal converter. What can we do? Let's try to see how it will react to load change. Take a look, I will double the load. This is average. Half a load, full load. One half. Do you see what changes? Can you tell what changes? You see how width of the pulse, its area changes. Length. Area of the pulse is amount of energy on each cycle coil will receive. So, half a load, we have this area. Double load, and you see how controller reacts. It doubles, in fact, area of the pulse, thus coil will have twice more energy, and voltage, look what's happened with voltage. Half a load, full load. You see, current changes, but voltage, you see changes in voltage. Let me tell you one thing. If you're not interested in my discipline, you understand? Why I'm wasting my time? Read the book, I can tell you. Do you think it came from the sky? Case in instant time. double load, controller changes the pulse width, and you can see voltage remains constant. It keeps voltage, of course in some load range, unchangeable while the load changes. I can show it from the other side. What will happen if I change primary supply voltage? Take a look. Now we have 24 volts and 1.8 amp. 16 volts. See what happens? Oh, it's a margin of stability. We can switch to average. Volt, 1.28. 16 volts, 1.96 amps. You see what happens with the pulse? Supply voltage decrease. Amount of energy load will receive also decrease. What controller did? Elongated the pulse. PWM controller keeps amount of energy supplied to load constant. This gives, what this gives? What this yields? Efficiency above 70%. Such system is very effective.
And where do we use the system?
All around. All around us. GPU, its power supply, here it is. Here is the coil, and these are switches. Take any motherboard. Everywhere where you see coils, it is it. Modern power, wait a second, modern power supply. Power supply. Example, power supply of modern electronics.
Let's say in each microchip these days we use this technique.
Each microchip in nowadays needs DC power and stable. So somewhere should be a power converter to supply power for this chip. Example, today's power supply. At the input, rectifier block. To supply, it will be 300, actual 311 volts.
Excuse me. The sign of diode inside in says that we have like diode on each basically on each side we have a diode or what?
Yeah, it's a set. No, it's integrated here.
Just
1 second, I have drawn like this, so it will be one diode, second,
I thought about that.
and number
so
4.
It just indicates that each side has a diode.
Yeah, it's a common symbol for bridge. It will, here we have 230 volts AC. At the output we will have 300 volts DC.
Can there be a variable power converter? So for example, from 24 to 12, but can we make for example, from 24 to 18?
Easy.
Like,
Easy, just shift a set point.
okay.
Easy.
I mean, in the circuits.
Yeah. Just turn this one. It can supply range from 5 to. It cannot. step down cannot supply voltage above its input. They are step up using self-inductance of coil. Also, such controller can be voltage inverting. It can convert 24 to -5. Yes, there are. Yes, PWM-based power controllers can also invert voltage. Wait 1 second, I will draw simplified schematics of this.
Where is this one actually from?
This one, cache register. This was a cache register. What I need to, yeah, it has a bipolar transistor as a switch, coil, primary coil of transformer. This will be plus 5 volts DC. Ground, it needs a snubber network. And key element of this, it's a PWM controller receiving voltage from the opposite side. It's via optocoupling. But it, in general, it controls the switch. Can I connect it? One second. I can disconnect this one. One moment, we will get nice diagram. But please don't do it at home. If DC, the small step down controllers are relatively safe, this one can easily kill you. 1 second, I will get my signal. This one goes here. This one goes here. Scope, where are you? It's a high voltage probe for school. here it is. It's a voltage of transformer. Just for understanding, each division, it marks 10 volts, but it's not at 10 volts. Because my divider, it's not 10 but 100. 100, 200 and 200 here. If you get this discharge to your head without this nice electric shocking machine, so welcomed by TV players, your brain will be dead in 15 minutes. Do not try to do something with such kind of power supplies without training. Small charger from mobile phone can easily kill you. This pulse through head means death within 15 minutes. It's really dangerous. Let's say do not try this at home. Okay, take a look. I'm changing load. Full load, half load. See how pulse width changed? This thing, it's a kind of controller. What it's do, it charges the transformer primary coil and let it oscillate. This was so-called quasi-resonance. Look how it reacts to voltage change. Full voltage. Now it's full 300 volts. See the area of the pulse. Half of the voltage, 150 volts. See what happens? Higher voltage, pulse narrows. You see? That's how pulse width modulator works. Width of the pulse changes to keep load voltage constant. I can show pure power supply. Where are you, my victim? What I did with the power supply? It's from the PC. AT and ATX power supplies have a different design. To get because they need more power, they often use a half-bridge design with two switches instead of one. That's how voltage of this double. It's a transformer voltage. See how it reacts to the change of primary voltage. It's need to keep output voltage constant. Less noise. And this are smaller. It has a softer computation. But again, you see how PWM acts. I change supply voltage, but modulator keeps amount of energy primary core of transformer receives on each cycle constant. Please don't try it at home without training. This high energy power supplies are real dangerous. And what we get from it, just for understanding, look here. I have two transformers. 1 and 2. This one is from PC power supply. It's for 100 rated power 150 watts. This for 50 Hertz. It's also 150 volt amperes. Without this technology, you have to carry this with your computer. This is for 50 Hertz, and this one for 150 kilohertz. For PWM driven power supply, and this one will be for ordinary. We will also 1984, 5 volts, 18 amps supply, only rectifier, and this one is stabilized. You see the power losses. You see cooling surface. Such kind of transformer will require such kind of heater just to dissipate power losses. Is a difference. Energy efficiency. That's why this technology is so needed. But everything pays. Everything has its cost, should I tell. We need power electronics, and there is another cost, noise. This power supply had only one output noise at 100 Hertz. For this one, long tail of high frequency components. Okay, I can try to show it. Maybe I will go back to small one, right? here is a sequence from my cache register power supply. Its amplitude going from the 200, 300, 500 volts. But I would like to see its spectrum. Here is my spectrum. Okay. I want to, maybe I can measure frequency. Yeah, I can measure frequency. As you can see, it should be 102 kilohertz. It's a conversion frequency. Now let's take a look on the spectrum. Maybe I can. Yeah. See the sine x divided by x like spectrum. It starts from the beginning. Here is 100 kilohertz, first line, and it ends at 4.5 megahertz. At such kind of power converter produce powerful and powerful and broad spectrum of noises. It's a problem when you deal, for example, with high range acoustics. And more problem, small signals like bioengineering and so on. This spectrum, it's on the first look, it's above hearing noise or above frequencies of bioprods, but in reality is more complex. It also disturbs communications. That's why there is a mandatory input. Here should be a special filter, capacitance to the ground, another capacitance to the ground, but the most to prevent network from the noises, a special B coil is mandatory. Without it, you will not get acceptance for sale of your device. Don't I have some? What? All their power supply disappeared. Oh, this one is not dead. It's from. This one is from TV set. Here is double coil and filter capacitors. This blue filter capacitors. And looking deeper, you will find another double coil. This flat one, you can see it's in two sections. It's a double coil. This one is double coil. This one has a double filter, double noise filter. Main transformer, and at the output, this is filter coil. Again, to protect from noises, TV internal electronics. Nice double coil. Here is rectifier. What else? This is over voltage protector. And set. These are primer capacitors. And for secondary part, diodes are under this cover. You can see them from the other side. These are diodes. nice flat power supply. I don't know, I have a lot of power supplies, but they disappeared somehow. But K is key moment. I can look on how it reacts. Lower voltage, spectrum is shorter. Higher voltage, because pulses are narrow. The narrow pulse means wider spectrum. And here pulses are narrowing, and you can see spectrum. For us, it's a spectrum of noises. Spectrum of noises. Okay? Low voltage, shorter spectrum. Higher voltage, longer spectrum of noises. And it looks like sine of x divided by x. I'm not sure, is it possible to find anything in our time without such technology? And it's what can be plugged from, no, not only plugged, battery power also uses PWM. You need to convert from 1.5 or 3 volts to voltage of microelectronics. All these converters are based on the pulse width modulation idea, because it allows to its idea how to keep amount of energy stable. See? Higher voltage, shorter pulses, lower voltage, longer pulse. Area of the pulse remains the same, amount of energy this transformer received remains the same. Everything under control. Rectifier, double coil, noise filter to prevent red line to spread all over the power network. And output, this one is output filter. Nice? Nice. Again, do not try to interfere with the power and based power supplies. I have special transformers, special test, and they are special prepared. Only trained personnel can perform maintenance. That's what is written on the where is my signal? Hey, signal, come back, please. See it in different time scale. It's a DC-DC converter, 24 to 12. It works funny. Charges capacitor, oh, I don't need to do anything. And stops. This one is full load model. And again, you see a spectrum like sine of x divided by x, and much wider when the spectrum of modulate. By the way, it's a bit funny. Input voltage, input current. 16 volts, 1.3 amps. 24 volts, 0.87 amps. What Ohm law says to us? Who remembers the Ohm's law? Yeah. Here, current is proportional to voltage. Yeah?
Current proportional voltage, yes.
Yeah. Current should be proportional to voltage by the Ohm's law.
Yeah.
Here, 24, 0.86. Voltage, 24 volts, 0.86 amps. $16 volts, 1.33. What did I have its voltage? Increased or decreased? Decreased. And current? Decreased? Increased. So what we see? Current is not proportional to voltage. Why? Because this thing is not a resistance. Its reaction to voltage is determined by control strategy of PVM. This thing is not constant resistance law, but it's much closer to constant power law. Controller tries to keep, see, 12 volts, 12 volts. I increase voltage by 8 volts, here 11.9, 12 volts. Controller tries to keep amount of energy load receives constant. So it takes, at the first, if we ignore losses, it takes constant, unchangeable amount of energy from the power source. That's why we see what it's doing. That's why we see not constant resistance as it should be with ordinary rheostat, but constant power. And current is not proportional to voltage. We see an opposite. We see current being something like 1 divided by voltage. Inside, if we take each element of the schematics, Ohm law will be enforced. It's okay. But for schematics overall, because it's active, it's not a passive circuit, it's active. And let's say performance or characteristics of active circuits are determined by its control strategy or control law, not by simple constant as it should be with rheostat. So here, if you want to kill your physics teacher, show a PVM circuit. Ohm law is not working. See how what a kind of interesting strategy it used. Half watt, full watt. Half watt. And I need full voltage It's not changes every pulse. Where is the stability margin? 15, 14. Okay, it's near stability margin. And you see spectrum, how it widens. It's all noises you will get for your schematic. There are many cases people caught. What a strange signal. Look, I have a signal from outer space. Idiots, it's your power supply. See, this sine x divided by x is all this long tail of waves. I will save energy. Yeah. PVMs are funny. They are step down, step up, and inverting converters. One moment. I will. Oh. 1 second, I will. Ratings. 1 second, I will find. I will find a possible application chart. Diagram. 1 second. Yeah, this one is. Uh-huh. One moment, I will bring picture. Hey. Yes. Here is the data sheet of controller tortured. Typical application, switch, regulator, reference oscillator, all kind of test date. Let's go forward. Application when you need a fixed voltage or adjustable voltage with the divider. In this version, output voltage is lower than the input voltage. Noise reduction, typical shutdown, it's not so complex. Version with delay. This schematics. It's a voltage inverter. From plus 5 volts you get minus. Easy. This one is shut down. Okay. So, if needed, it can produce also negative voltage. And if very needed, it can act as a boost. Buck is down. Inverting buck bust. It can produce. It can produce. Yeah, it can act as inverter if you need shutdown. So internal. Where is internal? Yeah. Here is, let's say, internal logic of this converter. Reference point, feedback voltage, PWM current, the shutdown, overcurrent protection, and it has ability for external on-off control. Simple. Effective. Key moment, where is the effectiveness? Efficiency. Yeah, take a look, typical. For 3 volts, 77%, for 5 volts, 85%, for adjust converting from 15 to 12, it will reach 88% efficiency. Not good. Or not bad. It is good. Effective thing. So, what's the conclusion? Up to 30. Input voltage from 4 volt to 40. Output can reach up to 35 volts. Useful thing. So, conclusion. Pulse width modulation, when applied to the energy control is something what our today digital reality stands on. Without it, complete failure. We will need to go back to these transformers. And you will not be able to carry your phone with you. Because processor power will have such size sinks, thermal sinks. It's not good. Okay. We have one viewer. I think my time for today has come to an end. I will end my stream soon. Yeah?